Swayam Prabha. Digital India. Educated India.
Welcome back. So, now we will look into the equivalent circuit of a transformer. To quickly recap, what we have seen is that instantaneous voltages across a single phase or a two winding basic two winding transformer, which is notationally shown like this. The current enters this dotted terminal primary, exits the secondary. The turns ratio are in the ratio of n is to n 1 is to n 2. Sometimes it is also written as A or A is to 1, where you are not specifying n 1 and n 2, but just specifying the ratio, and this is same as I 2 by I 1. This is, of course, we are doing AC circuits. This is not valid for DC, but is valid for all other waveforms which keep changing. So that there is a d phi by dt associated with them. And then we also saw that for an ideal transformer, V 1 I 2 I 1 star is equal to V 2 I 2 star. So, if the P plus jq enters this primary winding, the same P plus jq has to exit the secondary winding, the complex powers being equal. The next thing that we saw was that if I keep a transformer at ideal transformer at open circuit means no load connected to the secondary. Ideal transformer has I 1 equal to 0 and I 2 also equal to 0, but because of the finite mu r, which is finite mu r, even if large, which is associated with the transformer winding, I will have some magnetizing current which will be flowing through the source into the transformer, but I do not want it to flow into the ideal transformer. This is my ideal transformer. So, what I have to do is I have to give it another shunt path of impedance jxm, which is to say that Vrms divided by Irms is equal to the magnitude of xRms. And where is my Vrms and where is my Irms? This is my Im coming here. So, this Im by root 2 is going to be equal to Irms, and for this B there is a V waveform, and V is equal to j phi phasor wise, V is equal to n 1 d phi by dt. So, phasor wise V 1 phasor d by dt can be replaced by j omega. So, n 1 and the phi phasor. So, the flux phasor is going to lag, the flux phasor is going to lag somewhere, or the voltage phasor is going to lead the voltage phasor is going to lead uh, voltage phasor is going to lead um, the flux phasor by 90 degrees, which means that its identical zero crossing would have happened before 1/4 of time period before the zero crossing of the flux phasor. So, that is why I have shown this as this. So, therefore, this is the Vm, 1 by root 2 of it is Vrms, and we have plotted the Im also. 1 by root 2 of that is Irms, and the ratio of the two is the magnetizing current. This is not Im here does not mean the peak value, means the magnetizing component of the current, and the ratio of that gives you the absolute value of the reactance, which is Xm, when it is positive number, and J times of that is the magnetizing impedance. And then I am just showing here that after that, in our approximations that we are building up, comes the ideal transformer. Now, the next thing that will come to your mind is, is that what about the hysteresis, is it not? Because you know that the BH curve has a hysteresis aspect associated with it. So, let us say that this is the BH curve which is associated now. And as earlier, this is the B of t, phi of t, and therefore, by appropriate scaling the B of t, which is associated. And as in the previous thing, I am interested in the waveform I of t. So, again this curve is now a realistic BH curve. So, if you neglect hysteresis, even then you will I am now considering it as a nonlinear curve, but at one go I am also trying to consider the non-ideality also. Now, so let me say that initial point is somewhere here. When the B is 0, I have 2 points which are available. I am going to assume I am going to cycle through this again and again, is it not? So, what I am saying is that when the B is 0, this is the initial point which is there. So, this is point number 0, and this is the point number 0. So, the now if you look at point number 0, there is some current which is associated with this point number 0, because there is some H which is associated, and therefore, because you have to push this current to get B to 0 to cancel the remnant flux which is there. What we are saying is that there is a current which is going through here, and in fact this is the point where H is 0, but there is some remnant B. So, prior to that there has been a point somewhere here, we call it -1 if you want, where the current was 0. Now, let me say that we are moving in this particular direction. So, this is my first point, and I get the value of H, and I plot this current here. So, this point is the 0 point, this point is my 1 point. So, this is my 0 point, this is my 1 point, and then I take the next point somewhere here. Now, you have a feel of what I do when I do this thing. So, the second point comes somewhere here, and then let us take the third point has to come, the third point should match this. So, actually this one, this is like this, and so on the x axis, whatever is this displacement, that is the same displacement here, then whatever is the displacement of this second point, that is the displacement of the second point here, though it looks larger here, and then this is a quarter of a cycle displacement, and this is that quarter of the cycle displacement here. In the previous class I had directly plotted, I think, from here, but now I had to create this offset for this axis, because otherwise it would have become very messy. So, now if you plot, this is the way we have reached the peak current, and now while going back, for example, let us look at this point is incorrect, this actually is sloping like this, there is only one unique point there, but I am not going to correct that figure right now. While the going back, you can see that current is actually, like for example, if you are somewhere here, there is a higher current here, but on the return trajectory there is a lower current here. So, this point here, on the return trajectory, when I go by the same time offset, I do not get this value of current, but actually I will get for the same flux value. So, for the same flux value means after the same time offset, is it not? Because the flux value is pure sinusoid. So, if I have I have taken these points with certain time offsets, then when I am looking at the B curve, and then trying to interpret the time offset from there, the same time offsets are coming here also. So therefore, I can take whatever was the time offset from here to here, the same time offset I can take from this point onwards, but the current value was high. The current value was higher here, and the H value. Let me slightly modify this. It should be somewhat symmetric. So but the H value will be now, H value is higher here, but the H value is going to be lower here. So the current is not going to come back at that offset, the current is not going to be here, but it will be somewhat a lower value. And so you can see that the current waveform now is same thing happens here, same thing happens here, and so when the flux comes to zero value, the current becomes negative because it is sort of dropping down. So the current becomes negative, and I am bit difficult to sketch it now, but very beautifully. So I am just completing it for the sake of discussion, but is the point which I am trying to make is the waveform is periodic, no doubt, because whatever is traced in one cycle is going to be traced again and again. So therefore, it is periodic, but not symmetric. So you can see that if you do a harmonic analysis of this current waveform, Fourier analysis of this current waveform, it will have fundamental current component plus harmonics. We will have fundamental current components plus harmonics. And if it is a good piece of iron that you have picked up good properties, this area should be small, which means that harmonic levels should be low. So harmonic level should be low. So therefore, in our equivalent circuit that we are going to develop for this transformer today, in the equivalent circuit, we will ignore the harmonics only. So for example, on a digital storage oscilloscope, you can record the current waveform, then you can calculate the first harmonic and then look at V1 by I1, the first harmonic component or the fundamental component, and see this magnetizing component part. This ratio should be equal to JXM. I will come to that, what is going to be the JXM, but if you look at V is anyway your sinusoidal supply, and I1 you are taking the first harmonic component of it. When you take this ratio, you will get the magnitude of the magnetizing impedance, and it is going to have two parts associated with it. One part which is going to be associated with it predominantly is the magnetizing current, which we have discussed in our previous lecture, but the other component which is going to come there is going to be the hysteresis loss, which is arising because this is the amount of watts that you are going to lose per cycle with some proportionality factor, and I mean proportionality factor is only associated with area volume of it, because on BH curve whatever you get is joules per meter cube. So, you will have to look at the area of cross section, the length, and multiply by it to calculate what is the hysteresis loss which is happening with it, and then multiply it by the frequency per cycle, multiply it by the frequency, you will get the hysteresis watt loss which is occurring. Plus you also know that because the iron is a good conductor of electricity, so there is eddy current loss which happens along with it, and because of it we have to laminate the core. These are some things which I have, I think, discussed earlier when I discussed eddy currents and hysteresis losses. The laminations have to be aligned in such a way that the mica strip or the laminating part, the gluing part comes in between the current flow direction, so as to create a larger resistance to it, and so the lengths are elongated and the resistances are increased, and therefore eddy current losses are controlled. Otherwise, there will be severe heating of the iron, and a very lossy device would be created. So, all that if you measure, if you put a wattmeter for example, which measures the watts which are consumed by this device here, So, a wattmeter will have a voltage coil and a current coil. The voltage coil has to be connected in the shunt, the current coil has to be connected in the series, and then you look at the wattmeter reading, which is the average power which is dissipated per second. Then you will see that it will record the sum of eddy current losses and the hysteresis losses, and therefore, if I look at this reciprocal of this I will get the magnitude of the magnitude of the no load, the magnitude of two things. I'll write this as magnitude of a component which is resistive and a component which is inductive in nature. This resistive component is responsible for modeling, will help us model the wattage loss which is happening, and this component will help us model the magnetizing current which is otherwise associated with the BH curve. So, the reason I am writing it in this particular way is that I want to not write, I do not intend to write the Rm and Jm in series, I wish to write them in parallel. So, if I write it in parallel, then the net impedance, the reciprocal of net impedance, which is the net admittance, is going to be Y is 1 by Rm plus 1 by Jxm, which is Gm minus Jbm. So, let us put a minus sign for the time being here, time being here. The reason not to put this in series, but in parallel is to think that now I can write this current as the open circuit current, is to say that the open circuit current has two components. This is the mental makeup that I am making in an equivalent circuit, that the current has two components, one related to the active power current, which is related to the losses which is happening in the magnetic circuit, and one which is the reactive power current, which is related which is the reason for creating the, which is a consequence of the flux which is created in the core, and if the flux is created, then the magnetizing current has to be drawn, and that magnetizing current should be reactive, as we have seen in the previous class. So, the actual current is a superposition of these two components. So, if I have to superpose the two currents, then I should show them by two parallel branches. The open circuit current enters here, active power current component goes through this branch, and this this JXM, this carries the magnetizing current component. So, this this gives me this particular thing. Now, you take a reciprocal, I can measure I can calculate this, and I will be talking of open circuit and short circuit test later on, which will help us to understand how we measure these parameters. Then all I am trying to say is that, look, you can always convert this into calculate this net y, then take the reciprocal of it, and then that becomes the effective z, and that z has just r plus jx, which can equivalently be shown like this also. So, it is possible to convert a parallel combination by saying that y is equal to sum of g minus jb, look at the reciprocal, and then whatever is that impedance, show it as a series combination here, but it does not suit our modeling philosophy. It does not suit our modeling philosophy, because our modeling philosophy started like this, that first there is a ideal transformer, so no current is drawn. Then we said no, there is a BH curve with a high mu r, so some magnetizing current is drawn. Then we said no, there is a hysteresis and eddy current loss also. So, now an active current component is also drawn, and these each thing one by one, for each one of them we are trying to put a element, and so our open circuit current should be superposition of these two currents. So, therefore, the resistance and the magnetizing components, the resistance should be the losses should be modeled by resistance, the magnetizing current should be modeled by inductance, and because this is the summation of these two branches should come in parallel. So, therefore, you will see that in data sheet we will give this in the units of mhos. You know, this instead of giving you these values in ohms, we will give them in mhos, so that directly you can calculate, you will have GM and therefore RM, and you will have BM therefore XM. So, that is the idea. I hope it is clear. This you have to develop the intuition for this step by step. Now, let us come to the other effects which we need to model. What are the other effects that we need to model? First effect that we need to model, and all of you know this very well, is this the leakage flux. The leakage flux which is associated with the primary winding, and the leakage flux which is associated with the secondary winding. Now, how will a leakage flux be modeled? A current, series current, the leakage flux phi L is proportional to the current which is flowing. So, phi L1 is proportional to I1 and phi L2 is proportional to I2. So, therefore, the inductance component which has to model it is the leakage inductance L1 for the primary winding and the leakage inductance L2 for the secondary winding. Now, what is the way, what is the relationship? Now, the question that is coming is, okay, I know I have to model it as a inductance, but should I connect it in series or should I, like the magnetizing impedance, connect it in parallel? So, the thing that very important thing that you should understand here is that as the current in the primary winding increases, so proportionately the leakage flux has to increase. So, if you connect the leakage inductance of the primary winding in series with the in series in the equivalent circuit, so that the full current IL can flow through it, then automatically it will make sure that as the current increases, so does the leakage flux increase, and therefore, also the voltage drops which are going to associate with it. On the other hand, when you connect something in parallel, like the way I have done here, something in parallel like the way I have done here, what is the what really is fixed across it is the voltage which is there. So, let me now say that this is the leakage inductance L1 of the primary winding, and then of course, there is a resistance which should of the primary winding which should anyway come in series with it. So, because the more the current, more the IR drop. So, again the same principle is there, that the current, the drop has to be proportional to the current. So, therefore, the element everywhere where the drops have to be proportional to the current, the elements should come in series, and then I have Rm Jxm, and then the primary part of the ideal transformer, and this side looks to me to be the to the supply side. So, R1 in this the one subscript is indicating here that it is the primary winding, 1 is the primary winding and 2 is the secondary winding. So, what happens is a very small drop will happen in the resistance and the leakage. This is not going to be predominantly big drop. If this is a big drop, then your transformer device will not be very close to an ideal device. We will engineer the device in such a way that these losses are small. So, we will have usually thick enough wires, so that the resistance is small, and the whole idea of developing our transformer was to keep the leakage inductance low. This is at this point of time more like a parasitic effect. So, a very small value will be there. These numbers are going to be large, because we have designed thick enough magnetic core, so that the reluctance is actually the magnetizing current is small, and so the reluctance is high, and similarly the losses are small, which means the active power current component is also small, and so the ratio of V by Vs by I this is also going to be small. So, practically whatever is this voltage which is applied here would actually appear across this, independent of what the load, changing load which I have connected on the secondary side. So, by changing load, what I mean to say is, morning you have switched on geysers, nights probably you have not, it is a winter season, probably you have not even put fans. So, there is literally there is no load running on your house, maybe a refrigerator here or there, and come the day you start geysers, you start in the evening, you start lights, otherwise you start your computers, you charge your phones, you run your washing machine, you do so many things. So, the load which is coming across here is continuously changing throughout the day. But because these drops are small, almost this same voltage is getting impressed across your winding, across the winding. The flux levels really don't change much. The currents which are drawn here are literally same, close to the open circuit current values, and the losses also in the core are literally almost the same, they are not really changing significantly. Now, is secondary winding conceptually any different from the primary winding? No, it also creates a leakage, it also has a resistance R2, and it also creates a leakage flux which is proportional to the current which is flowing through in it, and after these drops have been taken away, whatever is available, that is available to your load. So, the V2 is here, sometimes we show this as even induced voltages, even E2 N1 is to N2 or A is to 1. The ideal transformer is sitting here, and now this is a reasonable equivalent and very commonly used equivalent circuit of a single phase transformer. So, again to quickly recap, you apply a voltage, a current has to flow because you have a load connected here. So, a current has to flow, that I2 current will be scaled down by I1 by I2 is equal to N2 by N1, which is 1 by A. So, I1 is going to be I2 by A. So, if this current is I2, I2 by A current will flow here, and there is some magnetizing current which is almost constant, which will flow here, and then this will become the I1 current which is flowing in the primary side. Okay, we have moved quite a bit of distance, and once you have understood the equivalent circuit of actually a transformer, later on you will find that induction machine, which I am going to treat it more as a generalized transformer, because there is a rotating element also going to be there, then a similar equivalent circuit can be easily put up there. So, this whole concept we are going to reuse it there, and in this the harmonic effects of the no load current have been ignored and adjusted, but the RMS value of the currents have not been ignored, because your V by I will do the open circuit and short circuit test and measurements of the parameters later. There you will directly measure the net losses, and V by I will give you the no load current, and then that is what you are going to split it into these two components. We can simplify this equivalent circuit further. We can simplify this equivalent circuit further. How? By two things. One, we are going to eliminate this ideal transformer in between, so that we have a simple RLC kind of a circuit, that is our aim to reach. So, we will use some trick and eliminate this ideal transformer. That will give us a circuit which looks more like a T circuit, this and some equivalent impedance here. And then we are going to say that because the no load currents are so small, do we, for normal work, day to day work, like if I apply this voltage here, if I connect a load here, what is the voltage here, do I really need to model this 1 to 2% small current? And answer would be, no, not really, not required. So, therefore, we will later on do a simplification that many times we can ignore this one also. But first thing first, let us see now what we will do is we will see the trick how we can eliminate this ideal transformer. So, to eliminate the ideal transformer, what I have to do is, let me take first of all and show you what happens. I am saying now, introducing you to a concept called as transferring impedance from secondary to primary. This is a concept that I am introducing. So, suppose this is a ZL, and now I am just going to say that the turns ratio is A is to 1, and I am connecting a primary voltage sinusoidal voltage source V 1, this is I 1, this is I 2, ideal transformer. I generally use X for abbreviation for transformer, and therefore, X MER I write many times for indicating a transformer. It is just my abbreviation. Transformer is such a big word. Okay. So, we know that this is V 2, this is E 1 or V 1, because it is an ideal transformer. So, this is also the V 1, or this is, let me call this E 1 only. E 1 and V 1 are the same. Let me call this as E 2 and this as V 2. E 2 is equal to V 2 and E 1 is equal to V 1. Now, I know that V 2 by I 2 is equal to ZL, whatever R 2 plus J 5 ohms, whatever, some R plus J X or R minus, whatever. This is V 2 by I 2. My question is, what is the impedance seen from the primary side? Okay. So, this is my question, and so I am really asking you what is V 1 by I 1, but now let us see what is V 1, what is V 1 by V 2, N 1 by N 2, which is equal to A. So, therefore, V 1 is A times of V 2, and this is same as I 2 by I 1. So, therefore, what is I 1? I 2 by A. That means, all the quantities on the primary side which are required for calculating the impedance, I am now trying to write them in terms of the quantities on the secondary side, because that is where I have everything available. The impedance of the secondary side is known to me. So, therefore, I am doing this, but then this is same as A square V 2 by I 2, which is equal to A square, this is my load impedance. So, therefore, A square ZL. So, when I transform, so I will say that the impedance as seen from primary is equal to square of turns ratio times impedance in secondary. Similarly, so if Z2 is the impedance, whatever it is, the load, it could be network and a load, it could be actually before the ideal transformer comes into picture, it is going to be this, is it not? So, this is ZL, the load impedance, and actually what is coming here? What is coming here is R 2 plus J X L 2 plus ZL, and this, suppose I want to transfer it onto the primary side. So, what should I do? I should multiply it by A square, that square of the turns ratio, and whatever comes here. So, if this whole thing is called Z2, then I am going to call Z2 dash referred to the other side as A square times of Z2, and the unit is ohms only, because the turns ratio is free, does not have any is a dimensionless constant. Once I do this, I can eliminate the ideal transformer. The current drawn is going to be the same, it is going to be the same. So, I can eliminate the ideal transformer altogether. Measurement instrumentation wise, if the primary was connected to this value, it is same as having a transformer which is connected with Z2. It is exactly same. If this is connected with Z2 here, and here instead if I just connect Z2 dash, the V1 and the I1 are not going to be any different. So, the source will not understand that array I have replaced the transformer by another equivalent impedance. That is the whole idea of equivalencing. Now, I will remove, therefore, what I will do is I will call R2 dash to be equal to A square R2. I will call XL2 dash as A square XL2, and I will call the load Z A square as the ZL dash, and since these are all in series, these are all in series, when I transfer it on the refer it, this is called referring it to the primary side, then multiply it by A square and eliminate this transformer. So, the equivalent circuit now is going to look like this: R1 JXL1 RM JXM, then R2 dash JX2 dash, this is A square R2, this is A square XL2, L is indicating leakage, XL2, J times of that, and then this is ZL dash, which is A square ZL. So, is the power factor depends predominantly on the power factor of the, this is where your supply terminals are, this is where your supply terminals are V2. So, this is where your supply Vs is, the power factor is this ratio of voltage by the power factor is this ratio of this voltage by this current I2 dash. Now, the current is also I2 by A, when I refer it to primary, it is also I2 by A, which is I2 dash. So, I will mark this as V2 dash, actually this current is V2 A, V2 is V2 dash. Now, everything in this circuit has now been referred to primary. So, you can see that it is easier to work with, this circuit, and this is the way our circuit is going to look like. Now, this is T, right, this is exactly what is T, this form is T. So, this is like a T equivalent of a transformer, this is like a T equivalent circuit of a transformer. And now, one final simplification, you can work with this, there is no problem with it, but these values are in practice relatively very small, and this value is usually very large. So, this component, if this is 100 amperes and this is 1 to 2 amperes, for most of my calculations, I can take this outside, ignore it and do a calculation as if the circuit, this is engineering now, this the engineering approximations. This is going away from your normal 12th class physics intuition and developing in you intuition about how to go about approximating things and simplifying it such that the results that you get are close to what is going to come out from physics, but the computation which is to be done is much more. So, this current is I 1, this current is I 2 dash. The magnetizing current branch which was here has been ignored. So, earlier correctly speaking I 1 is I 2 dash plus the magnetizing current component, which is I will call it as open circuit current component. But once you ignore this component, then I 1 is because I 1 is approximately equal to I 2 dash, then this series equivalent circuit comes in. Now, you can write R 1 plus R 2 dash together, J X L 1 plus J X L 2 dash together, and so you get R equivalent for the leakage, R equivalent for the net resistance of that is interposed by the transformer windings, X equivalent for the net leakage impedance which is interposed by the transformer winding, and a ZL dash, the load which is created here. This is your V 2 dash, this is your V 1, this is the current drawn, and so you get V 1 is equal to V 2 dash plus J times R E Q plus J X E Q times of I 1 or I 2 dash, whichever way you want to write it, and a very simple model comes out. Now, this parameter V 1 minus V 2 dash, magnitude of V 1 minus magnitude of V 2 dash divided by V 2 dash, this is actually the value, this is called as the into 100 actually is called the voltage regulation in percent of the transformer. So, if I say voltage regulation is 5%, then what it means is this numerator, the difference in the voltage at open circuit, V 1 is the voltage at open circuit, this is the V 2 dash is the voltage at the secondary terminals multiplied by the turns ratio to get this dash value, that is called as referring it to the primary under load condition. So, this indicates how much voltage has dropped when you applied the load because of these parasitic effects of resistance and the leakage reactance of the transformer. And this, to decide this 10, suppose I am getting 390 volts at the output and this voltage drop is let us say 10 volts, then I would say that I have two choices. Say 400 volts was applied, 390 was this is the input voltage, this is what is seen as output, means V 2 dash, means V 2 dash. So, the actual transformer could be like 4:1 transformer step down, which is transforming it from 400 volts to 100 volts. But this is then in that case this would be 39 volts, actual voltage seen is 39 volts. I have equivalenced it to the primary, and I have put this become 390 volts. So, I get 400 minus 390. Now, should I this 10 volts, should I compare it on should I compare it on 4 volts? Should I compare it on 400 volts on the base of 400 volts, or should I compare it on the base of 390 volts? We compare it on the actual voltage which is seen, which is 390 volts, and then this per unit drop. Now, what I have got is the per unit drop in the voltage, which is the voltage regulation, which I usually multiply by 100, and so this is going to be 10 divided by 390 into 100, which is approximately 2.5%. If you had used 400 at the denominator, then you would have said that the voltage regulation is 2.5%, which is what approximately we are saying, sir, this voltage device has a voltage regulation of, you will get a voltage regulation of 2.5%, means around 2.5% drop in voltage is going to happen. The reason not using 400, but using 390 in the denominator is that suppose this becomes only 200 volts and I use 400 volts. So, let us say that I got a drop in voltage, something extreme, 200 volts I got drop in voltage, then I would say voltage regulation is 50%, this will correspond to 50%. But if I use 200, then I will say that voltage regulation is 100%. Now, what is more serious? The problem is serious, and the gravity of that problem becomes more apparent when you use in the denominator the actual voltage output. As much is the voltage, so much has been the drop. This is not seen when you say 50%, but when you use denominator as 200 volts, you are saying that as much is the output voltage, so much 100% is the drop in the series winding, and this conveys the gravity of the problem more clearly. Hence, V1 magnitude of V1 minus magnitude of V2 dash divided by magnitude of V2 dash into 100% is called as the voltage regulation, and you are only comparing the RMS values of the voltages in this equation. We will have more of this discussion in the next class. Thank you.